Welcome to this fourth lecture in the programming language series. Today we'll be looking at types and polymorphism using Haskell as our example language. First, we'll review what are static and dynamic types in programming languages. Then we'll have a look at the concept of type completeness, what that means for programming languages and in particular in Haskell. And then we'll have a closer look at types in Haskell. Last week we had our introduction to Haskell, but we never saw a single type declaration, even though Haskell is statically typed, and we'll see how that works. Then we'll have a look at polymorphic type systems, and in particular what different forms of polymorphisms there are in programming languages. We'll be diving deeper into that a few lectures from now. Then we'll see how Haskell manages to get away with being statically typed, yet without requiring us to explicitly declare the types of functions and variables. And this is done with the help of the Hindley-Milner type inference algorithm. Finally, we'll have a look at overloading in Haskell and how that's used in connection with the user-defined data types. I'm using a variety of sources for this lecture. Once again, the classic article by Paul Hudak from the ACM Computing Surveys on functional languages and on Haskell. I strongly recommend you to read that article in detail. Briefly, I'll be making reference to another classic ACM Computing Surveys article by Cordelli and Wagner on polymorphism, and we'll be diving more into that, as I said, when we have a dedicated lecture on objects and types. And finally, Watt's book on programming language concepts and paradigms. So let's dive directly into the question of static and dynamic types. First of all, what is a type in a programming language? There are many different ways we can think about it. If we type in Haskell an expression like 5 plus empty array, the Haskell compiler will complain and say there's a type error there. But what does this mean? It says 5 plus empty list doesn't make sense. In particular, there's a mismatch. So the term 5, which is of type integer, doesn't match the argument which is of type list of something. So what's actually going on here? One way of thinking of a type is as a set of values. So the set of integers is the set of numbers, of negative and positive integers and 0. The type Boolean consists of the values true and false. Points are an unending list of possible point values. So that's one possible and sensible way of thinking about types. But there's another way of thinking about types. Think, for example, of interfaces in Java. When we declare that a variable must conform to the type which represents an interface, well, that interface doesn't have a set of values. Any class could implement it. So there's another notion of a type which is a partial specification of behavior. So, for example, when we say that n and m are integers, and n plus m is valid, but negation not of n is an error, it means that there's some mismatch in the behavior of n, which doesn't allow the logical negation operator to be applied to it. Similarly, if we specify that n is an integer, then we can assign an integer to it, but we can't assign a string to it. So a type can also be thought of not just as a set of values, but some kind of specification of what the function or the variable should fulfill. But what kinds of specifications are interesting or useful? Now, let's have a little bit of a closer look at different kinds of programming languages. We're used to talking about languages being strongly typed or untyped. I would argue that that's not the right way of thinking about programming languages. So a much more precise notion is that of static and dynamic types. In fact, any programming language, even the ones that we commonly refer to as being untyped, actually have a very clear notion of a type. It's just that in some cases, some languages have static types and others have only dynamic types. A value in a programming language has a static type which is defined by the language. A variable may have a declared static type. So when we write in Java the line applet myapplet equals new game applet, that's a statement, we're declaring the static type of the myapplet variable to be of type applet. That's the static type. Static simply means that we can determine the type by looking at the text, the program text only. So without executing the code, there is a static type. So looking at this code, we can see, okay, clearly myapplet, this variable, has the static type applet. Now, values also have runtime values, runtime types. So when we evaluate the expression new game applet, that's going to have at runtime, it's going to be an instance of the class gameApplet. Reading the code, we can see the static type of this expression. It's going to be a gameApplet. So just by reading the code, we can see what's on the right-hand side is a gameApplet, what's on the left-hand side is an applet. And because we have a notion of polymorphism, or subtyping in particular in Java, we can make this assignment, because a gameApplet is a valid kind of applet. But from the program text, anywhere else in the program, the static type of myapplet continues to be applet and not gameApplet. This is important. At runtime, however, the dynamic type of the value assigned to myapplet is something else. It's a dynamic type of gameApplet. So there's a distinction of the two. Now, what's the importance of static types? Static types restrict the kinds of programs you're allowed to write. Now have a look at this picture. This picture is a Venn diagram, and the big circle, the biggest circle, represents all of the programs that we might try and write. Some of those programs are syntactically okay. So there are some that are not syntactically okay. Those are in the pink zone, so they contain some kind of errors. They're programs, but they don't really make sense. They're syntactically wrong. Then, within that, we have programs that are syntactically okay. So they would parse. They look like valid programs in Java or Haskell or whatever language we have. But some of those make sense to execute and some don't. So, for example, it's syntactically okay to pass an integer to a function that expects an applet, but semantically it doesn't really make sense. So there's some semantic restrictions. On the other hand, there are lots of programs which are semantically okay, that make sense, but perhaps from the perspective of the type system, they're not okay. So the static type system is what it's going to do on the basis of the knowledge of the program text alone, without executing the program, tries to check if our program is semantically okay. Now what happens is, as a result, programs that are in the blue zone, they're semantically okay and statically typed okay. So the compiler will accept them, and it's going to allow us to run those programs. However, there's still a zone, which is the green zone, and these are programs that are semantically okay, but the type system rejects them. Let's take a look at the little snippet at the bottom right of the slide. In this code, we have a variable of static type object, and we assign to it the value of an expression which creates a new instance of the class cowboy. Well, a cowboy is an object, so this assignment is perfectly fine. We have a static type of Wyatt, which is object, and a dynamic type, which is cowboy. In the next line, however, we try and invoke the draw operation on Wyatt. The static type system says, well, all we know about Wyatt here in this line is that it's an object. We don't know anything about its dynamic type. Based on its static type, however, we know that there is no draw operation in the class object. So our static type system will reject this as being incorrect. So this is an example of a program that's semantically okay. It would run perfectly fine if the compiler would let us run it without raising any errors, but the static type system rejects it. Now, there are different kinds of programming languages. Statically typed programming language try and determine if our programs are statically okay based on the program text alone, and they will reject programs that they cannot guarantee are statically type-safe. A language is dynamically typed, notice not untyped and not weakly typed, but dynamically typed if only values have fixed type. So, unlike Java, if you have a language like JavaScript or Smalltalk or Ruby or Python, these languages are dynamically typed. You do not have any static type declarations. Variables and parameters take on different types at runtime, and they're checked. So there is a type check, but it happens only at runtime. There's a terminology of strong typing. So a language is strongly typed if it's impossible to perform an operation on the wrong type of object. But I would argue that's not a very useful distinction, because pretty much any language has a clear notion of types, so it doesn't make sense to talk of strongly typed or untyped, but more whether languages are statically or dynamically typed. Now, how do you check the type consistency? Essentially, there are three things you can do. On the one extreme, you do the compile time static type checking. On the other extreme, you do dynamic type checking at runtime. And in between, you can do another form of static type checking, which is based on dynamic type inference. Static type inference. And this is exactly what Haskell does. Here we see a variety of different languages, and we can categorize them as static or dynamically typed and strong or weakly typed. So even languages like Ruby and Smalltalk, which some people would call untyped, are actually strongly typed, they're just dynamically typed. Weak typing, however, happens in languages which are a little bit sloppy about their type checking. So in C, for example, it's possible to write programs which will break, crash at runtime because of type errors. Same happens when you write assembly code and you're sloppy about your types. But most mainstream languages nowadays are strongly typed. The only important distinction is whether they are statically or dynamically typed. Pretty much all programming languages provide some set of built-in types. So we have primitive types like booleans and integers and floats and characters and what you will. And you also typically have some composite types, so lists and arrays and tuples, maybe matrices, functions are composite types as well. In addition, most interesting languages give you, as a programmer, the possibility to define your own abstract data types, your own kind of user-defined data types. These include things like enumerations and recursive types, generic types, objects, classes, and so on. So much for the background. Let's take a look now at the notion of type completeness. So this comes from the reference by David Watt, the book that I mentioned at the beginning of the lecture today. He defines the type completeness principle as follows, that no operation should be arbitrarily restricted in the types of values involved. And this relates to the notion of first-class values, which we saw last week as well, and the notion in Haskell in particular of higher-order types. So the question is, what are first-class values in your language? The principle of type completeness says that you should try in your programming language to be as open as possible and allow anything to be a first-class value. Of course, no language achieves that entirely. So as we've seen that there are in Java, even though every object is first class, not everything is an object. So things like classes and methods are not really first-class values. We have representations of methods and classes in Java, but they are only second-class citizens. We cannot actually modify it or create a class at runtime in a straightforward way. Furthermore, there are other kinds of things like a statement or an expression is not a first-class value that you can pass around, nor is a package. But the type completeness principle says that you should, one design principle for your language that you might want to attain is to have as few second-class values as possible and as many first-class values. So functional languages try to make no class distinctions, whereas imperative languages typically treat functions at best as second-class values. So in Haskell, for example, we can see the type completeness principle in the fact that we have higher order functions. A function itself can be a first-class value. Okay, so with all this background, now let's have a closer look at how types work in Haskell. So here are our first types. We didn't see any up until now, and we could write and execute Haskell programs without paying any attention to the type system. A type is defined for an expression with double colon. So here we say that the type of the factorial function is a function type from integer to integer. And the type of the value 42 is an int. Taking these two facts together, we can deduce that the result of applying the factorial function to the number 42 will be an int. In other words, the arrow type int arrow int, we consume the first int when we apply the function to its value, because int matches with int, and then we'll get the result of what's on the right-hand side of the arrow. So the result will be an int. Now, we've seen that interesting functions tend to be curried, so any function that has a series of arguments will be interpreted as a curried type. So, for example, int arrow int is a curried type, and we parse it as follows. It's an int arrow, and it will return a function from ints to ints. When we write the expression plus 5, 6, it's parsed the other way. We first apply plus to 5, and the result is a function which can then be applied to 6. Now, taking these facts together, the fact that plus is of the arrow type int arrow int, in other words, plus is a function from ints which will return a function from int to int, and if we apply it to plus, well, apply plus to the value 5, well, 5 is of type int, so that will consume the first int, and the result of applying plus to 5 is going to be a function from ints to ints. This makes sense because we want to apply that to the value 6 and finally get an int back. So far, so good. We've seen integers and function types. What are list types? What's very elegant in Haskell is that the expressions for describing types, their syntax is very similar and mirrors that of values. So if I have a list of type A, then I write that as square bracket A n square bracket. So the value, the list containing the value 1, so bracket 1 bracket, it is of type bracket int bracket. So 1, the list containing 1 is of type list of integers. Note that the types are homogeneous. So lists must contain values which are all of the same type. I cannot have a list that mixes integers with characters and booleans or anything else. That's not allowed. Tuples are list-like things, except they have a fixed arity, and the individual values can be of different types. So I can have a tuple, for example, here, the tuple 1, list of 2, and 3. It's of type tuple of int, list of int, int. Second example is a tuple with the character A and the value false, and it's of type tuple of char and bool, and so on. So I can have also nested tuples. So here I have a nested tuple containing the pairs 1 and 2 and 3 and 4, and it's of type tuple of pair of int and pair of int. Very cool as well, the same syntax, open, close, round parentheses, is the unit value, and its type is written the same way. Notice we can never get confused between types and values, because values appear only in expressions that are executed, and types only appear in type expressions. Notice the limitation of the principle that we spoke of earlier, the type completeness principle. We would like everything to be a value, but a type itself is not a value that you can pass around. So a type in Haskell is not a first-class value, and a type doesn't have a type. Now, in most programming languages, there are ways of creating new data types, and Haskell is no different. However, the way you create data types in Haskell is a bit different from the way we're used to doing it in object-oriented languages. So how do we do that? You need three things. First of all, a new data type, you have to give it a name. That's fine. We're used to doing that in Java and Python and Ruby and all our favorite OO languages. Then you have a set of parameter types. So the parameter types are essentially the data that the data type holds. So here in the template, we see data, that's the keyword, data type name, and A1 through AN, the list could be empty, are all of the pieces of data that that data type will encapsulate. Finally, on the right-hand side, we have a set of constructors for elements of the type. So these are the things that we can create. Each of these constructors looks like a function. It's either a named constructor, where we have a name followed by a list of arguments, possibly empty, or it's a binary operator. And a binary operator is any sequence of funny characters as long as the first one is a colon. In fact, we've seen one already, and we'll see it shortly again. Each of these constructors serves two purposes. On the one hand, you use it to construct values, but, and this is important, you can also use it to deconstruct values. So in order to do anything with the data type, once you've encapsulated a set of values, you need to have a function which will deconstruct the values using the pattern matching way of defining functions. So we'll see how that works immediately. So the simplest kind of data type is probably an enumeration. They don't hold any data, they're just a fixed list of values. So here we have the data type day. It has no arguments because it doesn't hold any data, and we have 7 constructors. The constructors are Sunday through Saturday, or in ISO form would be Monday through Sunday. Fine. So any one of these constructors can be called, and it will give you a value of type day. In order to do something with that, however, you must deconstruct the arguments. So that means each of these constructors can be used as a pattern when you define a function. So here's an example. We have the function what shall I do, and it takes an argument of type day, and it returns a string which describes what I'll do on that particular day. So I pattern match sun, and I'll relax on Sunday, and Saturday I'll go shopping, and any other day with a wild card I'll have to go to work. Now, this very simple construct works also for more complex data types. So here we have a temperature data type, essentially a union type. A temperature could either be a centigrade value or a Fahrenheit value. So here we have 2 constructors, the centigrade constructor and the Fahrenheit constructor, and they both take as an argument a float value. Now we can define a function of type freezing, which will map from temperatures to booleans, and of course things freeze at the same temperature but that same temperature is encoded differently in the Fahrenheit and centigrade scales. So a centigrade temperature is freezing when the temp value is less than or equal to 0, and Fahrenheit when it's less than or equal to 32. Notice we can't do anything with the temperature value until we've pattern matched it, deconstructed, and pulled out the value. This is completely different from what we do in object-oriented programs, where freezing would probably be a method of the temperature data type. And then centigrade and Fahrenheit might be concrete subclasses of an abstract type temperature, and freezing would be implemented as a method in a different way in the two subclasses, centigrade and Fahrenheit. So we can do similar things to what we do in object-oriented programming, but it's done in rather a different way. Instead of having methods that belong to that are services belonging to a class, we have functions which deconstruct the data types using the constructors as patterns to match. Let's have a look at something a little bit more complex, a recursive data type. Here we're defining a data type tree, and notice for the first time the data type tree takes a type parameter on the left-hand side. So this will tell us it's a tree of a particular type, so the type of values that the tree holds. So it's a bit like a list. We don't just have generic lists of objects, but we have lists of integers or lists of booleans or lists of lists. So we need to know what the type is that this container holds. So we can see that the arguments, the type parameters on the left-hand side of the data type definition, they are actually type parameters that describe what types of things we can contain. Now, what's a tree? Well, a tree consists of leaves and non-leaves. So we need at least two constructors. So there's a leaf constructor, and a leaf will take as an argument anything of type A. So notice this is a generic description. We could also define an int tree, and then we wouldn't need the A parameter, but then our tree could only hold integers. The second constructor is a binary constructor, and here we can see that the constructor starts with a colon. So colon, caret, colon, we picked it deliberately to look like a branch in a tree, and it takes on the left and on the right two subtrees. So we have two ways of building complex trees. They're either nodes or complex trees with two subtrees. How can we use that? Here we define my tree as being a tree composed of leaves and subtree compositions. And below, at the bottom of the slide, we have a visual representation of what the tree should look like. Haskell provides a special operator called :t, which allows you to ask what the type is of a particular value or variable, value, or expression. So if we ask what the type is of my tree, it will say it's not a tree of A's, but it will detect that it's actually a tree of integers, because the leaf nodes all contain integer values. If we had stuck strings in there, it would come back and tell us that my tree is a tree of strings, or lists of characters. How do you use recursive data types? The same as we use other data types. Typically, for every one of the constructors, we'll have a pattern, and if we want to have a function over those types, then we'll have to use pattern matching to deconstruct the types. Here I have two definitions of the function that takes a tree and returns the list of values contained in each of the leaves. So there are two cases. Either the tree is a leaf node or it's a complex tree. So leaves of a leaf, we simply return the list containing L. So a tree consisting of a single leaf with the value L in it will give us the list containing L. If, on the other hand, I have a complex tree with a left and a right subtree, in order to compute the list of all the leaves, well, we apply leaves recursively to the left left-hand subtree and the right-hand subtree, and we concatenate them with the plus operator over lists. That's a perfectly fine recursive data structure, recursive definition of a function that will walk over a tree data structures. Now let's have a look at leaves prime. This does exactly the same thing, but in a rather different way, using curried functions. So leaves prime will take as an argument a tree T, and it applies a helper function called leaves accumulator, and it will pass to it T and an empty list. And that empty list is where we're going to accumulate all the leaves of the tree. What's the definition of leaves act? Well, that's defined in the where clause. So the where clause, again, will deconstruct the tree T in two ways. If we have a leaf node, leaf containing L, then what we return is L colon. Now, think a little bit about what the heck L colon could be. In the second case, we have a complex tree with L and R. We apply leaves accumulator to L and leaves accumulator to R, and we compose them with dot. Dot is function composition. So now the leaf accumulator is going to be applied either to a leaf node or to subtrees, and we're going to apply that to a tree T and pass into it an empty list. And this will give us the result in the end. This requires a little bit of thinking, but the key thing is you have to understand what dot is. We'll see that in a moment. It's function composition, as I told you. And we need to sort out what the heck L colon is. We've seen colon before. Colon is the operator to construct a list from a head and a tail. But functions in Haskell are curried. So the colon operator is taking a head of some type A, a tail, which is a list of type A, and it returns a list of type A. In other words, colon is a curried function. And because it's a curried function, we can pass in its first argument without giving the second argument. So L colon is going to be a function from lists to lists. Okay, I'll let you puzzle over it. It's an exercise that we'll discuss again in a little bit more detail in the question and answer session for this lecture. There's the function composition, and now let's pass on to the story of monomorphic and polymorphic types in Haskell. Languages like Pascal and C, so traditional imperative languages, have monomorphic type systems. Sounds fancy. All it means, what monomorphic means, is that every value, every variable, every constant, everything has one type. So the mono refers to one. Polymorphic, by extension, simply means that things may have multiple types. Monomorphic type systems are super simple. They're good for type checking, but they're bad for writing generic code. So, for example, in Pascal, you cannot write a generic sort procedure that will sort lists containing different types of values, because you can't talk about a thing that has many possible types. So a generic procedure is something which will take arguments of multiple types. That conflicts with the notion of monomorphism. Polymorphism, a polymorphic function is a function that will accept arguments of multiple types. We've seen lots of examples of those. The length function is a function which will take lists of any type A, and it will return the length of that list. Here for the first time, we saw before how length was defined. Now for the first time we define its type as well. So Haskell doesn't insist that we write these type declarations. It's good practice to do that because it's a form of documentation. When I see the line in red, I see, oh, length, it's a function and it takes a list of things of type A, and it's going to return an int back. Otherwise, I'd have to stare at the code to figure that out. You say, oh yeah, it's taking a list, and oh, that thing that's coming back is a number. The map function, which we also saw earlier, can also be defined, can have its type declared in a similar way. Map takes a function and a list and returns another list. What's the function? Well, a function is an arrow type from an arbitrary type A to some type B. And the second argument is a list. That list must be of type A so that we can apply our functions to it. And in the end, we're going to get a list of things of type B after applying the functions to it. So the type declaration, even though we're not required to write it, is a nice documentation. It tells us map takes functions from type A to B and lists of type A and gives us back a list of type B. Here's the function composition operator dot, and we can see in its definition that f composed with g applied to x is the same as f applied to g applied to x. So f dot g is the composition of f and g. But it also has a type. It's a curried type. It will take a function, f, which is a function type from b's to c's, and a function g, which will take a's to b's, and when these two are composed, we'll be mapping from a's to c's. There are many different kinds of polymorphism. The reference for this is the classic paper by Cardelli and Wegner, which I referred to at the beginning of this lecture. We'll not go into much detail today here, but in a later lecture we'll explore in a little bit more detail these four different kinds. I just want to briefly summarize that we can generally distinguish two classes of polymorphism. There's universal and ad hoc polymorphism. Universal polymorphism is called universal because for a given function or entity, the same thing will take different types of values. And with ad hoc polymorphism, it's more of a syntactic trick. So with universal polymorphism, there are two kinds which are very important for us. There's parametric polymorphism and inclusion polymorphism. We know inclusion polymorphism from object-oriented languages. It's just subtyping. We have an inheritance hierarchy. If we're expecting an object of an entity of type object and we pass it an entity of type cowboy, they're compatible. The one type is included in the other. With parametric polymorphism, the relationship between the types is rather different. They're what we see in generics in Java when we have generic classes in Java or in C++ or other languages. And in Haskell, we see it parametric polymorphism with polymorphic functions like map. Something different is going on there. It's polymorphic as well, but it's not subtyping. With ad hoc polymorphism, it's more of a syntactic trick. We have overloading, like we have in Java and C++. We can have a class that implements multiple methods with the same name, but they take different arguments. So it's not universal, because in universal polymorphism, we have one function that takes many arguments. With overloading, we have many functions that syntactically look the same, but they have different implementations. Coercion is also a form of ad hoc polymorphism. We're expecting a value of a particular type. We see it's the wrong type, and we convert it. We'll see in a little bit later in this lecture that Haskell supports parametric polymorphism, and it also has a very nice mechanism for specifying overloaded operators. But before we do that, let's have a look at Hindley-Milner type inference. This is the algorithm that allows us to infer automatically types of programs in Haskell without having to explicitly declare the types. Now, let's have a look at a simple example. Here we have the definition of the length function. The length function takes an empty list and returns 0, or a non-empty list and returns 1 plus the length of the tail. Just by looking at the structure of this definition, we can see that length is a function from some a to some b. If we dig a little deeper, we see that the a must be a list. So we can refine the arrow type a to b so that a is actually a list of c's, whatever c is. And if we look at the right-hand side, it's fairly clear that the result in the end is always an integer. So we can refine b to int. Now we've used all the information in the definition and we can't go any further, so we can conclude that the type of the length function is list of c to int, where c is a type variable. This is essentially what the Hindley-Milner type inference algorithm is doing. It's using the information in the definitions of functions, looking at the structure to find out the general structure of the type, and using the implementation details in order to infer what those individual type variables can be refined to. So essentially what we're doing is we're binding type variables to concrete types. Now, if we have particular information, for example, we know that the length function is of type list of a's to int, and the map function is function to list, then we can unify type variables to infer what the type of the expression map length is, and also what the type of map length list hello world is going to be. So map applied to length allows us to bind the type of length to the first parameter of the type expression of map. So in other words, the a arrow b is going to be unified with the type of length, which is list of a's to int. The result is then going to be the type that we see here. So map length has the type list of a's to list of int. Now, hello world, the type of a string is list of char, so the list hello world is of type list of char. Now, if we apply map length to the list containing hello world, char gets unified with a, because list of a gets unified with list of char. That gets consumed, and we get the result that's on the right-hand side. So we can deduce that map length applied to this list is going to return us a list of integers. The last thing I'd like to show you is a little bit more advanced example where we deduce, using Hindley-Milner type inference, the type of the map function itself. Here we're using the definition spread out in such a way that we can see what the parts are. And it's beyond the scope of this lecture series to go into the details of the Hindley-Milner type inference algorithm. All I want to do is to give you some intuition of how it works. First of all, let's look at the structure. So map is taking something and something else and returning another thing. So map is of type x, arrow y, arrow z. That's just based on the structural definition. So it's a curried type. We can dig a little deeper to figure out what x and y and z could be. So first we notice that our parameter x is being used in a definition and being applied to something. So that means x is a function type. Let's say from an arrow type from a to b, whatever a and b are. Good, so far we've used a little bit of information. We also see that the second parameter y is a list of things. So let's call it a list of c's. Maybe there's some relationship between a, b, and c, we don't know yet. Finally, we see that the third parameter z is also a list, so let's call it a list of d's. Okay, we're not done yet. Let's dig a little deeper. So, Now we notice f of x, the first parameter, which is of type A arrow B, is being applied to an element of our second parameter, which is a list of C's. So that means A and C must be the same thing. So let's unify them. So now we know that map is of type A arrow B arrow list of A. And finally, we see the result of f of x must be a b, because the result of applying f to something is going to be a b. And this is an element of the list in the result. So that means D and B must be the same type. So let's unify them as well. Now we've used all the information that's available to us, and essentially we're done now. So this is the type that we can infer for the map function. Hindley-Milner type inference is used in lots of modern functional languages. It allows us to reason about parametric polymorphism, but is not useful at all when we have languages with subtyping. So you won't see Hindley-Milner being used in this form for object-oriented languages with subtyping. You can also specialize types. So any polymorphic function can be explicitly assigned a more specific type. Let's look at the identity function, which takes a value x and returns x. That's obviously of type A arrow A, where A could be anything. But if we explicitly state that we want id int to be a function from ints to ints, then Haskell will accept that and refuse to let us to apply it to anything which is not an int. We can also use the :t operator in Haskell to query what the type is of an arbitrary expression. So here, for example, we ask, what's the type of the anonymous function which takes an x? So this is a lambda that takes an x and returns the list containing x. And the Hindley-Milner type inference algorithm will look at that and very quickly tell us, well, the type of that is A arrow list of A, where A is a type variable. If, on the other hand, we explicitly say that this anonymous function should have the type char to string, and we again ask Haskell to infer the type of this thing, well, then it will check and verify that this is a more refined version of the original type, and it will say, yep, that's okay, this is now of type char to string. In this case, A is char, and list of char is the same as string in Haskell. So the last bit of the story today is the story of overloading. Have a look at the following code. What's going on here? I can write 3 plus 4, so 2 integers, addition. I can add a float and an integer, or an integer and a float, or I can add 2 floats. And I can do this in most programming languages, I would say, probably all that I can think of. And probably in the first case I'll get an int back, and in the other 3 cases I will probably get a float back, or maybe not. I might get an int back in some cases. The question is, what's going on here? In the first case, I have 2 integers and I add them and I get an integer back, so that's integer addition. In the second case, I have a float and an addition and an integer. So that's probably float addition, and maybe the 4 is being converted to a float, or maybe it's a special plus operator that knows that one argument is a float and the other is an integer. So it could be coercion or it could be overloading. So the question is, do we have 4 different plus operations and no coercion, or do we have coercion and 2 different float operations, and what's being coerced to what? So in the first case, we might have addition for integers. In the second case, the 4 might be converted to a float, and we're using float addition. In the third case, the 3 might be converted to a float, or maybe the 4.0 is being converted to an integer. It depends. And then it might be either addition of floats or of integers. And in the final case, it should be addition for floats. Which is it? It depends on the language. So what's exactly going on can be very puzzling. As we'll see in a few weeks, the story gets very complicated in languages like JavaScript, which implicitly convert lots of things for you without necessarily giving you what you expect. Now, Haskell has a feature that allows you to define overloaded operators. It works differently from overloading in object-oriented languages, where you can simply define multiple methods with the same name that take different arguments. In Java, we can only have named methods that are overloaded, but in languages like C++, we can overload also operators. So we can define operators, multiple operators with the same operation name, but different types of arguments. So this is ad hoc polymorphism because syntactically it looks like the same operator, but they're actually multiple implementations. In Haskell, we define a class of operators. This has nothing to do with the term class in object-oriented languages. So it's not a class of objects, it's a class of operators. So these are type classes. So here, for example, we are defining a class for equality for a type A. It defines essentially an interface of two operators, equals equals and slash equals. The first will test for equality and the second will test for inequality. Each of these is a curried function, takes an A and returns a Boolean. The class gives you a predefined definition for not equals, and it's simply the negation of equals. So if you want to define equality for your class, then you'll get a not equals operator for free. However, the equality operator, you're going to have to define it. This is ad hoc polymorphism because for every type A, you're going to have to define the equality operator for your class. So we can instantiate this, as we see in the second snippet. Here we are defining the equality for Booleans. So we have instance equal for Boolean, and we define it as follows in the where clause. True is equal to true, false is equal to false, and everything else, true is not equal to false, and false is not equal to true. So in any other case, the answer will be false. Good enough. We can define equality for other types, but if we don't define it, it won't exist. So Haskell defines equality for integers, again with the where clause. I say we have an instance of equality, which will give us equals equals and not equals, and the definition is primitive equal for integers. Okay, it's a built-in. So the Haskell compiler, it provides us with a built-in library function, and the compiler knows what equality for integers is. And that seems fair. I don't think we should be given the task of defining that at the Haskell level. Now that we have equality for integers, we can leverage that to define equality for other things. For example, equality for characters. A character C is equal to a character D if their ASCII values are equal. So ORD C will tell us what is the ASCII integer value representing that character, and the same thing for D. Notice that the two equality operators we see on the second line there, the one on the left is equality for characters, and the one on the right is equality for integers. So the one is defined in terms of the other. Syntactically, they look the same, but they are two different operators. The third example shows us equality for pairs. So we can define equality for a pair AB if we already have equality for the types A and B. So this is what this implication arrow is. It says, I can give you an instance of equality. If you give me equality for A and equality for B, then I'll give you equality for the pair AB. Then in the next line, we see the definition, equality for a pair xy is equal to uv if, on the right-hand side, x is equal to u and y is equal to v. Here we see three different overloaded versions of equality. The one on the left is the equality for pairs. The second one is equality for type A, x equals u. And the last one is equality for B, y equals v. The last example here shows us that if we have equality defined for the type A, then for free we can get equality for lists of A. In particular, the empty list is always equal to the empty list, and an empty list is never equal to a non-empty list. And then the final case, two non-empty lists are equal if their heads are equal and their tails are equal. And that's going to be using recursion. So notice in the very last line, we are using only two overloaded versions of equality. The first one is the list equality, the second one is equality for the type A, and the third one is the recursive list equality. Now, you might ask, well, wouldn't it be possible for user-defined data types and any complex data types to automatically infer generate equality for all types of values? I mean, it's just recursion anyway. So here's an example which disproves that. Here we're going to define a new user data type called set, a set of A's. And the constructor for the data type set is also going to be called set, but it takes an argument for representing the values of that set using a list. So that's our constructor. Our constructor is set of A's. So I could write, for example, set, open bracket, 1, 2, 3, end bracket, and that's going to be a set containing the values 1, 2, and 3. Not a list, it's a set. However, its internal representation is a list. Now, we want to define equality for our sets. So if we have equality for the data type A that we're holding, then we can infer the equality for the sets of A. And how are we going to do that? Well, in the obvious way. We want to check that the two representations hold the same sets of values. Notice that we could not possibly infer that because syntactically we have no idea what the constraints are going to be. So what we want in the end is if we have the set 1, 2, containing the representation list 1, 2, 3, that should be equal to the set whose representation is the list 3, 2, 1. They are the same set of values. It just so happens that internally the representation looks different. So that means that our equality operator for sets needs to figure that out and needs to check that the lists actually contain the same set of values, even though their internal representation, the order of the elements, is different, because the order is irrelevant to us. As a final remark, we can't guarantee that equality makes sense for all possible data types. For example, if we ask Haskell the following question, 1 equals, that's a curried function, equals is a curried function, so 1 equals, what's that? Yes, it's the function which will compare its argument to 1 and tell us whether it's equal to 1 or not. It's essentially the same as the anonymous lambda, which will take an x and compare it to 1. So these two things are equal as functions. However, if we ask Haskell, are these things equal? There is no equality defined for functions, and for a good reason. Equality of functions is undecidable. It's equivalent to the halting problem. If we could solve equality for functions, we could solve the halting problem, but the halting problem is known to be undecidable. So that concludes this lecture and our introduction to Haskell. Next week, we're going to jump back in time and have a closer look at the lambda calculus, which is giving us the foundations for languages like Haskell, but also providing us with a number of very important concepts which will help us understand the design of other programming languages in general. Thanks for your attention.